Hello. Now in this part of the lecture, we need to discuss about how to estimate parameters simultaneously with the state vector. This is the situation that we have now. We have a state equation and an output equation. In the state equation, we have certain parameters in this vector alpha, and we also have certain parameters in this vector beta. I'm talking about parameters that we don't know with proper accuracy. There are maybe other parameters which you do know perfectly or with very good accuracy, so we don't need to be afraid about those. But we do have certain parameters which we may have certain idea about the value, but we don't know with proper accuracy. So we want to refine, we want to tune those parameters. So our state equation and our output equation will be better. So the better are these models, the better are the result in our estimation process. We don't need to have exact model because we know that this is unfeasible. There is no way to have a perfect model, but we try to improve our model if that is possible. So there may be cases in which the modelers are involved in certain parameters, but we don't know the parameters pretty well. So in that case, we have this question: could we estimate the state of the system as we used to do before, and in addition try to refine to estimate certain parameters? And they put here, they could be parameters that belong to the or are part of the state equation or output equation. Could we do that? So we could learn or at least tune those things. And then we mentioned some particular case which is clear for us. So suppose this case in which, yes, we are estimating the pose of the platform. That is what we are doing in project 2, part A1. And we did also in project number 1, but now we are doing this using Kalman filter. And yes, we had this state equation, our kinematic model, which is okay. We know how to deal with that. We know that this input vector is composed by two components. In our case, for our particular kinematic model, we have the longitudinal velocity, that component of the velocity vector, which is the speed for us, and also the heading rate that is coming from the gyroscope sensor. And this is coming from a speed sensor, possibly from encoder in some of the wheels of the car. And all of them, they do introduce certain noise because those are sensors. So we know that we are feeding those input to our kinematic model, and that does introduce issues. That is what we had in the previous discussion when our topic was the Kalman filter having a prediction step in which we have a state equation for which we assume there are certain uncertainties or certain noises polluting our state equation at each step. We knew also that sometimes it's because we are feeding inputs which we do know not perfectly, because we are getting those from measurement, and measurement are from sensor, and the sensor introduce noise. This is what we know. But some of these, in this case, the measurement from the gyroscope is coming with certain noise, and the noise is not what we would say is a white noise. Why is that? Because it has certain component or certain behavior that is like a constant, plus certain fluctuating noise. There is a model for that type of noise here. So we measure the heading rate, and that is equal to the actual heading rate plus certain constant values, a bias, plus certain fluctuating component, which is unknown. This is unknown, and this is also unknown. But this one is fluctuating, behaving as Gaussian or as white noise. In some cases, it's like a white Gaussian noise. In the case of the gyroscope, certain model, they do behave in that way. But also they introduce some bias, and this is definitely not something which is white. There is a strong correlation between the value of one sample time and the other, because simply it's constant. So if we knew the value at a certain time, we will know the value at different times. Of course, we never know this value because we are not in condition to measure that. But still, we know that there's no white noise. And many of the methods that we are talking about here applied in general, the Bayesian theory for doing Bayesian estimation or Bayesian sensor data. In that, using those approaches, we are assuming that the uncertainties on the noises, they are behaving like white noise. But this is not the case. So we know that there is certain bias. It's a constant, or it could be something that is changing very slowly in time. So if we had the good luck that we knew this value, bias, then we could improve our measurement just getting the measurement from the sensor minus the bias. That will be equal to the actual value of the heading rate plus the fluctuation, which is actually behaving as a white noise. So we got rid of the effect of the bias. That would happen if we knew that. In certain cases, you could do some offline calibration, which are good for a certain amount of time finally, and you could apply that. In certain applications, you don't have that advantage. You cannot do any calibration. And our approaches, I repeat, were okay if the noises or the uncertainties that were involved in polluting our source of information, if those sources of uncertainty were white noise or white Gaussian noise if we are using a Kalman filter. And we know, okay, I repeat here, our heading rate is polluted by a bias. So there is no way that we could apply the Kalman filter directly if this bias is a relevant number. It's a value that is supposed 1 degree per second, then we wouldn't be in condition to run the Kalman filter properly because we are really breaking the assumption that the uncertainty is behaving as a white noise, or in particular for the Kalman filter, white Gaussian noise. All right, so we need to deal with that. So could we estimate this, I put here, online? Could we have a real-time process in which we are in condition to estimate the bias? And the answer is usually yes. In our case, it's going to be the case under certain conditions, which we're going to mention in a moment. So what could we do now? Well, we need to expand or to augment our state vector now, adding an extra component, which in our case is the bias. So now we have 4 components because we want to estimate everything here. The original pose, X, Y, and phi, and now in addition, B, our bias. And then we need to propose a state equation for that, which is very similar to the one that we had before in respect to the component X, Y, and phi. But for the component corresponding to the bias, well, it's trivial, but it's new for us. It's telling us that the bias at time k plus 1 is equal to the bias at time k, because in this case, we are assuming that the bias is constant, plus nothing. That is our model. We need to add here some extra term in the model describing the evolution of the heading. Yes, because now we know that the variation of the heading will be the heading rate, which we measure, but also we are subtracting the bias because we want to compensate that. This bias is actually the real one. Okay, the compensation will be perfect. In any case, we are subtracting this, which is because it's the best guess we have about the bias. All right, that is our new model. This is assuming that, repeat, our bias is constant. So what is going to be now the covariant metric? Well, the covariant metric should be 4 by 4 because now our state vector is 4 by 1. And all the elements here, this submetric, the first submetric, the first 3 by 3 submetric here, that is, or similarly to before, is representing the marginal PDF about X, Y, and phi. And this one, P44, is describing the marginal PDF about element number 4 in the step vector, the bias. And all these other elements, they are modeling the statistical dependency between these and the other 3. Yeah, this is what we have here. Yeah, so we have a new covariant metric, which should be 4 by 4. And by, of course, our expected value now will be 4 by 1 because that is the dimension of our state vector. And how is now our output equation? Well, our output equation is very similar to the one that we had before, because in this case, we are assuming that we are measuring the range to the option of interest and also the angular position in our car coordinate frame, which is alpha, for which we have an equivalent expression using the position and the heading in the global coordinate frame. That's good. So that means that this output equation are function of the state of the system, X, Y, and phi, pose of the platform in the global coordinate frame, which is what we are estimating. They don't involve any participation of the element B here, but in general, we are saying this is a function of the state vector. It happens to be that this is function just about X and Y, and this is function only about X and Y, but no, and phi also, but no function of B, the bias. That is not a problem. Our system will be still able to estimate the 4 components because our system is observable. So we have this output equation, and then you ask me, okay, how is going to be the H metric in this case? Well, the H metric will be very similar to the one that we got before. If we have in this case in which we are measuring, or we have the output equation involved with the range and the angle alpha, I will get the analytical expression of the Jacobian of the output equation respect to the state vector. And of course, you're going to have 4 columns because we need to do the partial derivative of the range respect to x, y, phi, and the bias. And I also need to get the same for output component alpha, component number 2, respect to x, y, phi, and the bias. And if we are just doing what we do in project number 2, part A1, our output equation is simply the range. So we get this equation for which there is no mystery because we do the same that we did before. It's going to be very similar to the one that we got before. But now we have an extra column here, column number 4, which is capturing the partial derivative of this and this one respect to component number 4, bias. And of course, it's going to be equal to 0 because they are no function of that. We got the analytical expression, and we know how to use this analytical expression of the Jacobian of the output equation when we implement the extended Kalman filter update. So what we could say about the R metric? Well, the R metric is the same one that we got before because the R metric is just describing the covariant is the covariant of the noise polluting the measurement of the output variable. So that is identical to what we got before. The effect that we are including an extra component in the state vector, the bias, doesn't affect at all that thing. The covariant of the noise polluting the output variables, measurement of the output variable, it's the same one that we had before. What could we say about the prediction step? Well, now the state equation is this. We do know that because we did discuss this before. The important thing, okay, I need to implement the prediction. This is the state equation, the nominal one. So I need to also calculate the Jacobian of this state equation respect to state vector and the Jacobian of this state equation respect to the input vector, because I need those in my implementation of the prediction. And then we got those one. Yes, no problem. I will get the Jacobian of the state equation respect to the state vector, to the component. And here is, I express this in this way. And then we are doing the partial derivative of each of the component. We have 4 components, the one describing the change in x, y, phi, and bias. And I have to do the partial derivative of each of these components respect to x, y, phi, and the bias. So I do this. And this is the first 3 columns here. They correspond to the same that we did before. But now we have this column number 4, in which this is the partial derivative of this equation respect to component 4, component bias. And it's 0 because there is no participation. The same for this one. Now for this one, yes, there is participation of the bias. So the partial derivative of the component, which is describing the variation of the heading, is function of the heading itself in the previous time step. And it's also involving the input, the heading rate from the gyroscope, minus the compensation, the bias. So if I do the partial derivative of this respect to the bias, because this is multiplying here the delta t that we have in our Euler approximation. So we have minus t here. 0, 0, 1, yes, because I'm doing partial derivative of this respect to phi is equal to 1. And minus t, yes, partial derivative respect to the bias, multiplying here t and negative minus t. And finally, the component of the Jacobian, which is the partial derivative of the component describing the evolution of the bias in our state equation, and that will be 0, 0. There is no participation of x, y, and phi, and it's equal to 1 because it's equal to itself, the identity. So this is what we got. We are talking about the state equation. And this is 4 by 4. This is 4 by 4. What is 4 by 4? Because my state vector is now 4 components. And because my state equation has 4 components, okay, the Jacobian will be 4 by 4. It should be. Now, what about the Jacobian respect to the inputs? Well, that is different because now we have 4 components, which are function of 2 components. In that case, the Jacobian will be 4 by 2. That's okay. Yeah, because we do the partial derivative of each of these 4 components. The partial derivative respect to each of the 2 components of the input vector, respect to the speed and respect to the heading rate. Okay, those are the input that we get from the sensors in our state equation. Okay, that is why I'm saying here that this is 4 by 2. And you do the calculation because you will need to do the partial derivative respect to B and W of these 4 components, which is going to be very similar to the one that you got before, but you have some extra now row here. Yeah. How do we initialize this process? Okay, I need to propose an initial expected value and an initial covariant metric. Those are describing statistically what we know or our belief about the initial condition of the system. With respect to X, Y, and Phi, we already know how to do that, but what about the bias? Well, I need to propose something. They told me that the bias could be any value, suppose, for my gyroscope, between minus 1 degree per second to plus 1 degree per second, suppose they tell you. Well, I don't know what is going to be the value, so I propose an expected value equal to 0. I don't have any other guess. That's no problem. What about the covariant metric, the initial covariant metric for our system, our estimation process? Well, depending on what I know about the initial condition, initial pose, this could be plenty of 0, no? In project number 2, we are assuming that we do know that perfectly. So this submetric here, which is the marginal covariant, or the covariant of the marginal PDF about X, Y, and Phi, well, that will be plenty of zeros. If we have certain uncertainty about the initial pose, yeah, we'll put some values here. This is the other, which is important, because if I don't know the value, and I know that it could be between minus plus 1 degree per second, suppose that is a standard deviation, well, in that case, I may propose here this value. Or someone tell me, I don't know, it's uniform between minus half a degree plus half a degree. Well, I don't know. It could be any value in that range. I'm going to play safe. I'm going to say that this expected value is 0 and standard deviation 1 degree per second. I'm converting to radian here because in my program I'm using radian. Yeah. So that is what I propose here. This is very important because we have to tell the Kalman filter if you are convinced about what you are proposing in the expected value or you are not. If you put 0 here, the estimation process will say, you already know that, that's it. We are not going to touch this. You have to put some distrust. You have to tell the Kalman filter that you don't trust completely about your expected value, initial expected value about the bias. That is why we have to put a value here. That is this is repeating what I was talking about in the previous slide. What about the Q metric? Remember, the Q metric is the covariant of the uncertainty polluting our state equation in one step. Well, the rest of this will be similar to what we had before. No worries about that. But now we have a Q metric, which is 4 by 4, in which this component 4, that is talking about how confident we are about the component of the state equation, the component number 4, the one which is describing the dynamic of the bias. If we do know that the bias is constant and we are completely sure, so our model is perfect. If we have this situation in which we propose this nominally and we are completely sure about that, this Q44 will be equal to 0 because we are completely sure that our model is perfect. But it may be the case that it's not. Okay, so in this case, we are saying, oh yeah, I'm completely sure, so this will be 0. But suppose, no, but this bias is changing slowly, but it's changing. Now in a short interval of time, maybe 1 minute, 2 minutes, it's not going to change, so we don't care about assuming that it may be changing. So we could assume that Q44 is equal to 0 because we know that the bias at time k plus 1 is going to be identical to the bias at time k. But now we are trying to maintain this for a long run, so we need to tell the estimation process, watch out, this model is not perfect. The actual bias may change. And then you have to put a small value, a very small value here, just to allow the estimation process to catch up and learn that parameter in situation in which may be changing slowly in the future. Yeah. And I propose here something. Suppose, okay, the bias is usually almost constant, but I could appreciate that in 10 minutes, it may change, suppose, 1 degree per second. So in 10 minutes, if I have bias equal to 0 now, it could be that in 10 minutes the bias will be 1 degree per second. It's not going to happen suddenly. It's going to happen gradually. Not necessarily linearly, but it's going to be gradually happening. So I could propose that usually it will be changing. If it does change, it will be changing at this rate. I'm going to put here 1 degree per second. I'm expressing this in radian. I divide this by this duration of 10 minutes in second, will be 600. And I'm going to multiply by the very small amount of time between samples in our discrete time model. So if that sample time is 1 millisecond, that t will be 0.001. And I could say, okay, if the bias is changing, it's going to change 0.001 multiplied by this, which is also a very small value. But it's good that we're including that because we are applying this prediction very frequently. We are applying the state equation for prediction very frequently, every 1 millisecond. And even if that thing is very small, it will be adding something. So it's good to consider that. If we do that, our estimation process will be in condition to tune, to readjust dynamically to the bias which is changing slowly. And that it would happen in reality because our gyroscope will have this bias changing slowly. If some change in temperature happen in the area of operation, the bias will be changing slowly. That is why we should not assume that it's constant, except we are doing an experiment for a very short period of time, like what we are doing in project 2, part A1 or A3. And what is going to happen? It's going to, it's estimation process in condition to estimate that. And we are going to appreciate something. We're going to propose some initial guess equal to 0. And suppose in this case, the bias was 0.3 degrees per second. I'm showing this in that way. It's going to catch up. It's taking some time. It's going to learn that thing. It will have some small fluctuation, but it will be second order, error in comparison to this big magnitude. Assuming that is 0 will be not good at all. Trying to catch up with the actual value, even if we don't learn this perfectly, suppose it was 0.3 degrees per second, but that was close enough. That is a very good improvement in our system. And yes, we're going to see that thing working because I have a video about that in which I'm showing my solution for part A3 of the project number 2, and it does perform well. And you may ask, how is that possible? Because you are just measuring ranges and they are just function about X and Y. How could it be possible that we are estimating X, Y, and also the heading and the bias? Even in part A, we were in condition to estimate the heading. We were not concerned about the bias. Always because the system is observable. And because due to this combination between the state equation and the observation equation, the function, we are producing some statistical dependency. In our belief about the state of the system, there is a statistical dependency between X, Y, phi, and the bias. So if we measure output of the system, which are just function of X and Y, we are in condition to estimate heading and the bias. And that is because that combination of output equation and state equation make our system observable. And this concept of observability is something that you know from linear system and control. And also some of you are doing MTRN 3020. But you do this for LTI system, linear time invariant system, and you have a closed form. You have the observability metric and you verify, remember the rank of the observability metric. And if that was full rank, that metric, you knew that the system was observable. We don't have that advantage here because our system is non-linear. There is no observability metric, but we could do this empirically. We are going to verify that empirically we run this process and it's going to learn. And in addition, the covariant metric will be bounded. It's not going to be diverging. So because the system is observable. If our platform is moving just a bit, our system will be observable. If the platform doesn't move stationary, the system will be not being conditioned to learn the bias. But in our case, our platform is moving through the factory, through the hospital, and so it will have the opportunity to learn the bias. As soon as the platform moves a bit, The system is observable, so we are in condition to estimate all the state vector, including the bias. And you may ask, where is that statistical dependency in my estimate? I have a PDF, which I'm approximating using a Gaussian PDF, so I have expected value and a covariant metric. Where is the statistical dependency in there? Well, that information, or the statistical dependency, is in the covariant metric. Assume that the covariant metric is not a pure diagonal covariant metric. You have a statistical dependency between the component of the state vector which we are estimating. Yeah. And that is what does allow us to perform the estimation of the full state vector. And that statistical dependency, I repeat, is coming to the contribution of having that state equation and that output equation. And everything is stored in the covariant metric. We are done with this, and we are going to have a video talking about how is the performance of this type of estimation process, which is what you're going to implement for part A3 of the project number 2. I will show you that solution, my solution, because I did solve in the same way that you did. I proposed all this problem, but I decided to start from scratch just to verify there was any issue, because I proposed this new API and many things. This session I was doing everything from scratch. So the same example that I gave you at the very beginning, using the data, I got those ones that I published, I implemented before, and I did modify those, and I was solving on project 1 and project 2 part A1 and project 2 part A3. I'm doing the same that you are doing. I'm following you the same trajectory you are following. Okay, we are going to finish this discussion now.